Exercise 3.8. Let X be a topological space and let a subset Y of X have the subspace topology from X. And then part A. If A is open in Y and Y is open in X, show that A is open in X. Okay. This is sort of a transitivity property for openness, right? If the first is open in the second and the second is open in the third, then the first is open in the third. All right, now we can begin by saying since A is open in Y, well, what does that mean? Right? By definition, that means there exists some open set U in the large topological space X such that A is just the intersection of that open set with the subspace Y. Right? You see that in the picture up here. If we have A open in this subspace Y of X, what that means is that there's some open set U in X such that A is just the intersection of that U with our subspace Y. Okay. But the nice thing here is that, okay, U is open in X, but we're assuming that Y is also open in X, right? So A is just the intersection of two open sets, and therefore it must be open. Okay. Let's just write that down. Thus, A is the intersection of two open subsets of X. Hence, A is open in X. And that does it. Now the good news is, part B here, we're supposed to prove the same thing for closed sets. And the proof is so similar, I'm just going to copy our answer to part B and make changes where necessary. Okay. So since A is closed in Y, there exists a closed set, and use a bad letter for a closed set. How about D in X such that A equals D intersect Y? This is a theorem that we recently stated. I believe it was theorem 3.4. And okay, thus A is the intersection of two closed subsets of X, right? We said D is closed in X, and by assumption Y is closed in X. And the intersection of two closed sets is closed. And we're done.